Very good afternoon to every one of you. I am extremely happy to share my experience in this area with your colleagues. And so the topic for today is resilient seismic resistant design of buildings. The first point that we need to understand is what is resilient is all about. So let us start understanding what a structure is. A structure is designed, as you know, as per code, for dead load, live load, and all other load that you get across. So you design a structure and then build it, and then a structure is there in place. But what is resilient is, in addition to all the loads that we design for, there are also some kind of expected or unexpected things that can happen. For example, we have a code on earthquake, so we can expect earthquake load to be there, and there can be a tsunami if your structure is very near, and then can be flood due to rain, or temperature due to fire, or hurricane, or the cyclone wind forces, or maybe a shock or blast. So there are so many other aspects of possible loads which may occur in the structure during its lifetime. So what the important point is, this structure should endure, adapt, and quickly recover from all these cases uh, when a structure is subjected to any type of loading. Because initially we may think that it is dead load and live load that makes an issue, but there are other loads that we are going to talk about, and then that is what is very important so that your structure is safe. So this let me say that there are two possible understanding of the lateral load that can happen in a building other than dead load and live load. So the earthquake and wind forces can act as a lateral load in any structure. That is the first point that I want you to note. As far as wind force is concerned, there is a kind of uniform pressure and maybe non-uniform pressure as well that can engulf in the building. So let me say roughly the area into pressure, maybe the force, horizontal force that can exist. It can vary along the height. That is a different issue, but that is the first point that is there. Very similarly, earthquake also is a lateral load that is computed through some formation or whatever. So the idea, the first point that we need to understand the difference between these two is wind load as per the code if you calculate, and we design the structure to be linear and elastic for this throughout its life of the structure. Whereas when it comes to earthquake, it is not so, because earthquake is a very high force. I will explain why it is. So it is much beyond what we compute in a code. That means the structure will experience a kind of nonlinear behavior, and in spite of nonlinear behavior, your structure should be safe. So roughly saying, so for example, if you take a beam, the bending moment at the two extreme points may exceed the level of linearity, and it may go to plastic range. And similarly, it can happen in column also. So how nicely you design such a way that the structure does not fall during or crack or damage during its uh, earthquake region. So the question is, there is something else that happens. That means the structure goes to non-linearity. However, the deformation is going to very large level, but still they are safe. So that is given by another parameter called ductility. So the structure, in addition to strength-based design, for example, you design for dead load, live load, and earthquake load, wind load, whatever load it is. What you want, the idea is the forces that are coming in each member of your structure is safe, and the strength of these members against bending moment or shear, as the case may be, are well within the limits of its strength parameters. So that is the first thing that we need to understand. In addition to that, there are other parameters like stiffness, which means how much it can deform. For example, within the linear range, for example, it is nothing but load by deformation or whatever. That is what is called stiffness in the initial elastic range. So that is also to be governed in the design parameter. So coming to earthquake, so earthquake, in addition to all this, there is also called ductility. That is how much it can deform laterally without any failure. That is also an important parameter. So we need to understand what is the stiffness that you are going to keep, what is the strength parameter that you are going to keep, what is the ductility that you are going to keep. So it is a little complicated, but however, we will limit our discussion to what is given in code and how do they take care of all these parameters in simple. Suppose assuming that you are going to follow a code like IS 1883 or 3920, whatever that code you are going to follow. So in that code, how these three parameters are engulfed or integrated inside, and how we have to see this as a designer. So this is a first point. So okay, now the important question that arises is, suppose you take a building and you first check for what is the earthquake load that is coming, and you now check for what is the load that is coming in due to wind. So there are two things. That is, what is the earthquake load that is coming as a lateral load? What is the wind load that is coming in the building? So let me say that, for example, wind load is governing. That is the in one case, in any one case, wind load is governing. So the normal tendency of a designer is, so wind load is governing, earthquake is none of my business. But interestingly, please understand, earthquake may come, cyclone also may come. Only thing is, your design is governing wind load, so it is okay. So that means you have to take the design as a, we take the wind load and then go ahead for the design to find out the reinforcement or whatever. But coming to ductile detailing, we need to detail as per the Indian code. We need to do ductile detailing as per IS 13920 for concrete structures and IS 800 for steel structures in all the zones 3 and above in the Indian continent. Only thing is, they say that zone 2 is optional. For example, Bangalore is in zone 2. So there are some cities where there are zone 2 also is there. So here it is an optional. But interestingly, optional is not a choice. In my opinion, all the building, if it is crossing certain floors like 5 floors, 10 floors like that, wherever it is better to detail, because earthquake may come, but the only safeguard that we have is ductile detailing. That is another important point that normally people miss. So that is why I am highlighting. So let us now come to understanding what is seismic load is all about. So seismic load in any building is something simple, but the reality is the building is shaking. That is the reality. And how it is shaking? For example, it may be shaking for a few seconds, and or it may be shaking for a minute or maximum of two, not more than that. So it may be shaking violently, or depending upon the intensity of the earthquake, it may be more or less, as the case may be. But it is a very complicated phenomena because the loading is random, because there is no uniform G level that comes and there is no frequency content. So all these are funny things to happen. So in order to make this simple for a designer, so we adopt a rule of Newton, which says force is equal to mass into acceleration. So that is the simplest rule that you can ever think of. So okay, what is mass is all about? Mass is nothing but the seismic weight. That is the dead weight of the building. So in simple terms, that is the way it is. Maybe certain portion of live load also is to be taken. So that is the mass. So weight by G. So that is first part. The second part is acceleration. What is this acceleration? Because acceleration, even the real earthquake, it may come from some level to some other level. Because it is complex, we try to identify that by a simple term called peak ground acceleration, or PGA. So what we are trying to say is, whatever happens in the acceleration, whatever is the peak acceleration, you try to pick up that. So this is what is the concept that is behind any of this design or structural analysis. So this is the first point I want you to note. So we are trying to approximate a dynamic event into a static event, which by giving an equation F equal to ma. The question is, when something is moving, does all the mass of the building participate? Obviously, the question is, answer is not. So there is certain mass that participates, certain mass does not participate. So we will not go into all that. So for the purpose of design, we need to say it is a seismic weight. That is the thing. So coming to acceleration, so this in simple terms, there is something called base shear, which is VB, which is nothing but AH into W. W is nothing but the weight of the building. AH is some parameter. So the AH parameter, let us not so go deep, but however, just for formal sake, let me say it is nothing but ZI SA by G by 2R. This is the number. So Z is a zone vector that is given in the code. Depending upon the zone you get some number. Importance factor is, suppose you are building a school or colleges or some hospital, you give little more important than that. So that is the way importance factor is getting. SA by G is the kind of G value that really the amplification factor that we get for the G value depending upon your structure. Suppose your structure is 5-story, some number. If your structure is 10-story, it all depends on the period of the structure. So that is what is SA by G, which is given in the Indian code. There is another parameter called R, that is called response reduction factor. So that means that is also given in the code, something like 3 and 5. So what I am trying to what I want to look at this is, it is not some simple formula that we just compute and then go ahead. That is first thing we need to understand. So it is, though it is as simple as FA by F equal to MA kind of thing, but there are a lot of things that are happening in the history of earthquake that we see from 19 70s to till now. For example, the code continuously varies. This is the third or fourth version that is going to come in draft actually. So the way in which we see the zone, for example, the current code talks about four different zones that are given in four different colors in the left side figure. But the right side figure shows the draft code, which again increases the number of zone in a different way. What I'm trying to say is, for example, an earthquake happened in Latur and Killari that was in the lower zone. Actually, the whole earthquake should not have come there. So what we did at that point of time was 1990 or whatever, 94 or something. So we created 2001 time we created the zone map and then it is changed. So currently, depending upon the various information that we get, various knowledge base that we get, we try to change the seismic zones continuously. This I want you to keep because everybody try to argue saying that a code gives some number, so I will follow. Please understand what is the significance of anything that is given in the code. What is the possibility of likelihood of a variation that can happen in the code also is very important. That is the important thing that I want you to note that. So similarly, for example, if you see the current code, zone 2 means zero point 0.1, zone 3 means 0.16 and so on. So this is a very simple zone factor that is given, roughly saying the number varies between 0.1 and 0.36. Suppose you take the current draft code. Suppose the draft code, if you take, there is already the zone is increased to 6. And interestingly, they are going to give a different concept to you, saying that if you understand what is the return period of your structure, you can design accordingly. For example, if you understand it is only 73 years, something different like that. So what I'm trying to say, let us forget about all that. Let me say that assuming that this current code is to be compared with the draft, then the current code assumes return period is 2475 years. So if you take that, for example, zone 2 is now instead of 0.1, it is 0.15. And let me say zone 5, it is instead of 0.36, it is 0.6. And there is one more new zone added, that is 0.75. What I'm trying to say is the draft code already says the zone factor that is given in this code is almost twice to thrice is being increased. I want you to note this. This is the first point I want you to note this. Even though you are bound to design as per the current code only, but you can keep in mind that there is possibility of exceeding this force is a reality. So that I want you to note that. So for example, if you are looking for a building in Calicut, as per the existing code, it is only 0.16, whereas in draft code, it is 0.3. That means nearly twice. Let us come to Chandigarh. So the existing code says it's about 0.24, which is now revised to 0.75. That means nearly 3 times. So this is, I want you to note this just for fun. Anyhow, as a designer, we have to only go by existing codes. I know that, but however, it is better to remember that there are something that is happening in the making. For example, let me say that zone 3 I am taking, and I use this old formula, then I get a factor of 0.4. Suppose if you use zone 3 formula, it is 0.72. That means we are getting the force nearly 1.2 times more than what is really given in the current code. I want you to know this because suddenly, we say that the wind is governing, earthquake is governing, all that. So, but however, even if you understand the draft code, the force that is to be designed is nearly 1.8 times in terms of Chennai zone. In the same case, if you are looking for Chandigarh zone, so it is if you take ZI by 2 or all that, if you take, it is not 6 in the as per the current code, but if you use the draft code, it is going to be 0.18. That means nearly 3 times. So this is what I want you to note. So that means the force that you are computing today in Chandigarh is some force, let me say X, but if you are going to follow the revised code, it is going to be 3 times the force. You should understand these kind of funny things that are happening because if you go back maybe in the previous code, still it does slightly different and lower. So what I'm trying to say is, as the time goes, as the knowledge base increases, as the technology increases, and the understanding of the seismic behavior of the earth is understood better, so we are trying to increase the forces. So this we should keep in mind because suddenly we cannot revise the building which is designed for old code or something like that. For example, there is something called hazard conversion factor, which we normally in India uses Z by 2. That means 0.5. But if you see how the whole world sees, for example, American code sees this 0.5 as 0.66. European code says it's about 0.58, as our draft says 0.625. So our draft is very near to international standards right now. So this is just to say that our drafts are very near to international level, high level codes. Of course, this is one point I want you to note. See, this is the code given thing. We are having two different spectrum. One is for static load, another is for if you are going to do some dynamic analysis. This, in simple terms, this is nothing but SA by G. What are the values that looking for SA by G is given here, depending upon the natural period. Suppose you are having a 10-story building, which may be approximately about 1 second. So you have to go here, and there are three possible ways. One is rock or hard soil, medium soil, soft soil. So depending upon whichever you use soil type, you have to choose that number, and correspondingly SA by G values to be taken. So the top one is for static value, the bottom one is for dynamic thing. So another point I want you to notice these three categories. So suppose you are building a building in Chennai. Suppose you will say that what is your type of soil, whether it is rock or hard soil, or a medium soil, or a soft soil. So this configuration is also a serious problem. I want you to explain. I want to explain to you a little better on that. For example, the draft code talks about different classes, site A, B, C, and D, and all those things. So we will not. I'm just for introduction. I'm doing that. So forget about that. That is not our very much interesting to us. Another important point I want to notice. Okay, our code gives something like 0.1 G to 0.36 G, which is called peak ground acceleration, assuming that that is what is happening. But our own experience in India, if you take 1967 Koina earthquake, the recorded PGA was 0.63 as against what is to be given. So similarly in Killary, the peak ground acceleration recorded is approximately 0.5 G. So if you see this interesting thing, so if you see Koina, it is zone 4. So our code gives 0.24 G. That is the way code gives. But the really recorded G value is 0.63. Same way in Killary, the code says 0.16 G as of the existing code I am talking about. But the corresponding PGA that is recorded is 0.5 G. This also we should keep in mind. So that means I am not saying that you should design for more forces. Please don't mistake me that kind of thing. You should design only as per code. There is no doubt on that. But only thing is you should keep in mind that the real forces that are going to come in the building is likely to be more than as high as 2 to 3 times what you're seeing here. This is a real experience. And you should know this. This is the only thing. How are you going to take care of this is what we are going to see in this rest of the time. So, for example, in addition to that, we are again making it only 50% of that. So, Z by 2. So, if you are really seeing, we are only designing for 0.12 G as against 0.63 G felt. We are going to design only 0.8 G as against 0.5 that is felt. That is recorded. That is not felt. It is a pure record of Indian earthquake instruments. So these are the points that we need to keep in mind when you are coming to designing earthquake, because we can't simply follow some numbers and then go ahead. Okay. So now the question is, assuming that the forces that are really coming is higher than what is normal, and the new code, draft code, is also going to give nearly 2 to 3 times the force that is going to happen. Future floor can take care of that. But what happened today? Yesterday, what happened? So what is the way in which we are taking it? So in order to understand that, you need to understand concept of ductility. For example, if you have a building and you apply a lateral force and then try to find out the lateral deformation of the building. Let me say that you are applying a force to the top of the building and try to find out the lateral deformation at the top of the building. Let me say like that for the time being. Suppose if you put a curve like that, that is what the curve that you are seeing here. So the question is, the first question is, the structure is going to yield. The first point is that. So we are not afraid of that. So yield is not a serious issue at all. So post yield, every member is going to be nonlinear, and within that nonlinearity, the deformation is going to prolong longer and longer. So before failure, we put a line and say that is what is called maximum deformation, allowable deformation, or maximum performing deformation. So the ductility is nothing but the maximum deformation divided by yield deformation. So this is a simple understanding. So anyhow, really speaking, if you're really able to understand this and design, that is what is called performance-based design, you are able to do that. But since we are not up to that level, we will stick to what is given in the code, how we are going to take care. So to that extent, we will understand. So this ductility, how it is taken care, is a very important point in any seismic resistant design, which is the only thing that is available to you to save the building post earthquake or survival or something like that. So how this is taken care? For example, ductility is taken care because it is very tough understanding for common engineers. So what they are saying is, you don't worry, you simply reduce the forces. For example, we have two systems. One is called ordinary moment resisting frame, which is normal design structure. The other is special moment resisting frame, which is nothing but you follow all the rules of IS 3920. That is the only thing. So if you are following all the rules of IS 3920, the thing is called SMRF, that is special moment resisting frame. There, the forces that you are computing is divided by 5. Please understand that. That means you are divide. That means there is also another 2 there. So if you multiply 2 into 5, that is 10. 2R, that is 2R, that is 10. That means you are designing for a structure which is 1/10 of the force. It is an acceptable factor. Don't worry about that. But you should keep in mind, that's what I am saying. Similarly, if you are not going to ductile detailing, you should apply a factor of 3. That is 2 into 3 is 6. So you are designing for 1:1 by 3/6. But as per the latest regulations, it is better, except for zone 2, you always go for SMRF. In zone 2 also, wherever possible, better adapt. So this is the because we don't know when the earthquake come, where comes all that. So this is the first thing I wanted to note. The second point I wanted to note is the impact factor is given as 1.5 and 1.2 depending upon the rise of building. For example, hospital, schools, and all those things are given higher importance factor. That means you have a little more force for, because assuming that hospitals are patients are there, school and colleges are very, our next generation is there. So we are worried about that. So we try to design for higher this thing. But all other residential building and other things, we just use 1.2 or 1 as the case may be. That means we don't give any importance factor as the case may be. But here also the draft code talks about 1 and 1.15 only. And they are now reclassifying it based on return period and then various occupancy and so many things. So we will not go into that. I am just for fun, I am taking it. But the next important point is drift. So drift is nothing but what is, now that we are saying that the lateral deformation is allowed. So how much is allowed? How much I can go for? That is actually, this is going to define your initial stiffness. So this is how the stiffness is coming into play. As I said, stiffness, strength, and ductility are 3 parameters, and the stiffness, how it is, because stiffness, if we really compute and do nicely, it is good. But in the design code, we cannot give all that. So, but here also I want you to note that 1893 talks about 0.04 as elastic displacement. And whereas these Eurocode and ASC, they talk about amplified deflection. That means they account for some kind of nonlinearity that can happen. So they try to amplify and then do that. So this is, I just wanted to note that, but however, we can't do anything about foreign codes. But assuming that we are going to follow our code says the elastic displacement at the top of the building should be limited for the design load. For whatever design, that means design load means which includes dead load, live load, earthquake load, all that. So that is the first point I wanted to note. And another thing is, there is also, suppose this is only for high-rise building. This is not for a normal building. Suppose you go 40-story, 50-story, and all those things. So in that case, the P delta effect, that means the vertical load, which is now shifted because of the lateral movement, and the P into delta, if it is going to approach the lateral forces into height, then there is kind of stability problem. So this is a very additional point that we need to note in addition to all that. And this rule is applicable only when the building is very high, for example, 30, 40 stories and above that. So below that, this will not come. However, we need to do a check like this and then ensure that you are well within the safe stability. This is to ensure that your building is stable. So that is the way it is. So, however, in the draft, for example, Indian code, current code says the drift should be not 4 times height. That is the way it is. So delta story by delta H story. That means if you look for each story also, each story deflection divided by height of story is not 4. Or if you look for full building also, it is the total deformation of the lateral deformation of the building divided by total height of the building should be not 4 or less. That is in zone 4. But this is the current code talks about. But what is the future code talks about? Our Indian code draft talks about if it is zone 2, it is okay. If it is zone 4, you just reduce that. You understand that? That means the building is supposed to be a little more stiffer. That is what they are trying to ensure that in the revised code. Similarly, in zone 5, it is only not 2.5. That means it's still more stiffer. And if you are in zone 6, it is only not 2. That means still more stiffer. So this stiffness is brought as an independent parameter only in the future codes. So this is, I want you to note this in your mind, because currently this is not in rule as per the current code. But current code, what it talks about? The current code, it talks about whichever be the zone, the lateral drift should be not 4. So that means the higher stiffness that is required for higher zone is not taken care of as far as the present code is concerned. So this also you should keep in mind. Now we can't do anything about it because that is how code is there. But however, we should also remember there are certain, because we are first technology first, code second. That is the concept that I am trying to drive. And the draft code also talks about, suppose you have some building which is called floating building. Suppose in the ground floor there is one column missing, but still you project as a cantilever and then go ahead. So the drift is limited for this kind of building. It is only limited to not two. So this kind of thing is not there in the previous thing. That is why we have seen a lot of buildings that failed in Ahmedabad, Haryana earthquake that happened is mainly due to this kind of buildings which is normally defined as irregular. So the general point that we need to note is 1893 is generally for regular code, the regular building. So similarly, suppose you have a soft story in the ground floor, which is the stiffness is very less compared to the next stories, or in between, suppose you have a building which has more column height than the other corresponding floors. So these things will create trouble. So in this building, you should have a stricter rule saying that the story shift should be not two kind of thing. Or if you are able to take care of this soft story or the intermediate soft story building, it is better. So that is, you have to take care of it. The question is very simple. The rule of the game is very simple. That is, the stiffness between any two floors should not vary more than 80% or something like that. So only 20% variation is allowed between two stiffness between. This is the code allowed, code I am talking about. But if you are still better, it is good. So the question is sudden variation in stiffness. For example, stiffness is nothing but only a L cube. L is the problem. So because EA is maybe the same thing. So that is the first point I wanted to note. Similarly, now I'm coming to the next important point that I want you to note. The question is, for example, Indian code talks about three cases, that is type 1, type 2, type 3. And they simply say it is rock, medium soil, soft soil. But how do you know anything about that? So for the time being, you have no idea. For example, how do we go about? The only thing that you get from soft soil report is N values. So the rock, the site says N value. That also, suppose you should go minimum of 20 to 30 meters to understand what is really happening. Suppose in the top 1 meter you have greater than 30, and the next 10 meters it is less than 30, and the next 10 meters it is less than 11 or whatever. So suddenly you cannot say because you are resting your building in rock, you are in rock. That kind of wrong information is a very misleading thing. Why I'm telling all this is, if you are not modeling this, your drift value computation is wrong. So that is the first thing that I want you to note. So what is the better way of doing it? The better, because for example, people normally design go by N value. From that N value, they go by SBC, what is something else as safe bearing capacity. And you say your safe bearing capacity is safe against all the loads that you are getting. Your building is safe. Please understand it is not in case of earthquake. Because what I'm telling is, the way in which, how do you take the topsoil? Topsoil, suppose let me say 10 meters, 5 meters, you have more than 30. So you call it rock and then go ahead. The rest of the 5 meters, suppose if it is less than 10, then that will affect actually. That affects the building because you may not know. Because we cannot, just because the foundation is resting on a particular place, the bottom point is not taken into account is not point. That is the first point I want to note. Second point is, they are talking about something called shear wave velocity, because there are a lot of equipments that nowadays coming, this SASW variety of tests that are possible today with the scanning. There are so many new equipments that are coming, which is going to estimate the shear velocity for the first 30 meters. So we have something called VS30. VS30 is like shear velocity for 30 meters. So there are non-destructive equipments that are coming in the market. So we can do that. So this is slightly better way of taking into account. Because normally, we go by SBC value and N value. In my personal opinion, they are misleading. That is my personal opinion in the field. So unless you are very careful, you will be misleading, and that this can create a lot of trouble in reality. So one of the alternative way is, suppose you assume that the shear velocity should be more than 400 meters per second for the top 30 meters, then you can certainly call that as rock. There is no doubt on that. Similarly, between 200 and 400, you can call that medium. Less than 200, soft side. So this is the important point I want you to note. Instead of simply saying that you call that is soft, depending upon wherever your foundation ends. Wherever your foundation ends does not mean anything, because the whole load can be distributed to deeper depth where the N value can be different. The formula given in the bottom is a very rough formula. I don't want you to follow that. However, because you have no idea, I want to follow some formula means you can take this. That is the only thing, because there are only some what you call empirical. So they, based on some experience, they get that. but they can be erroneous as much as 100%. Please understand that my personal experience in this formula is we have experienced error of nearly 100% to more than that also. So these are all points that I want you to note, because suddenly, because we think that everything is fine, is not fine. But so what other country people are doing? Other country people are doing, for example, Eurocode is talking about 4 different sites. New Zealand is talking about 5 different sites. American code is talking about 5 different sites. Only Indian code is talking about. So this is also we need to think about. So what are we really missing? For example, Indian people are always go by SPTN value. See, SPTN value is the most misleading number you can ever think of in civil engineering. I am not discouraging you, but you can check yourself by doing some other way of understanding that. For example, from N value, you can find out the VS value, and then really you do a real shear velocity test of VS30 and estimate in that real site. And if you see in American code, Euro code, New Zealand code, everybody insists that you should go for shear velocity test, and then from there only you have to understand the classification. What are the classification you want to make? But we are the only people we go by SPT value and N value, and SBC people SBC value. We don't even talk about unconfined shear strength. We don't talk about so many other period issues. We don't talk about all that, because earthquake is a very complicated phenomenon. It is better to go to that kind of level. But however, I am happy to note that the draft code includes all these interesting things. So anyhow, since we are in the current scenario without that, so we need to go about that is a so this thing. So our draft code talks about 5 different values with the VS values, VS30 values, with the 1500 for A, the 760 to 5500 B, and so on. So this is the new change that is happening in there. Suppose if you are able to follow this, it's good. Even if you follow the current code, my request is go to try to find out the VS values, and then correspondingly find out 1, 2, 3, whatever. Like, because current code talks about 1, 2, 3. So whatever one you want to talk about, that also, you please go ahead. Another important point that I want to highlight is, far as the earthquake design is concerned, because I am not saying in general. Okay, in general, what happens? So in general, what happens is how you say that the applied load, factor load. So let me say applied factor load coming in each of the column or whatever footing is safe against SBC values. That is safe bearing capacity. You say you are safe. So this is the first way of understanding, because your argument is because how do you compute this safe bearing capacity? They try to find out the bearing capacity, ultimate bearing capacity, and divided by a factor of safety called to 3. And then you are already applied a factor of safety 3. So the safe bearing capacity is safe. This is what you think. But if you take in terms of earthquake engineering, it is not so. Please understand that. So in earthquake engineering, we need to understand that if you are going for doing a design of overturning, you should have additional factor of safety of 2 in addition to whatever SBC is. So if it is sliding, it is about 1.75, and bearing, it is about 2.5. So this is the if you are using static method. If you are doing dynamic method, maybe they are insisting 1.5. This is given in draft code. So you may argue currently this kind of rule is not there. Yes, currently this kind of rule is not there. That is okay. But we should understand these are all the way in which these are all the reason why we are not able to understand the drift values. We are not able to understand the failure. Why should our buildings fail? Like for example, in the Ahmedabad, hundreds of multi-story building fail in spite of the reason that they are all designed by some code that was existing at that point of time. So we cannot escape saying that no, the force was more, slightly more, that was more, this was more. All those funny things are apart. Our idea of resilient is the structure should withstand all the shocks and kind of thing that is likely to come in the structure, and then say that is safe. That is the first point that is there. So this is the main thing that I want you to note as far as foundation is concerned. Another interesting point that I note in the foundation as per my personal experience is, if you go by our Indian code, they talk about some minimum percentage that is given in not 1 to whatever. So I'm not going to talk about that, but please understand there is something called that kind of thing that is given in our code. Then you say that, because most of the time that the forces that are coming and the size of the foundation that you keep, if it is individual footing, invariably the design end up in minimum, because the kind of building one that comes, you don't take about the ultimate load, you don't take about many things that are talking about. So it may end up in not 1 to which the Indian code says. But interestingly, your AC 3 talks about not 1.8 as the As they are trying to give so many reasons, I am not going to explain that. But one of the reasons that they give is the repairs to foundation is difficult and expensive. Better to have a little more. So this is maybe a crude rule for you. But interestingly, there are so many things that, like for example, we are not taking care of factor of safety for the foundation for various actions like bending moment or direct forces, whatever. And and that is a very important thing for me, in my opinion. So designing a foundation to include overstrength factor or increase seismic demand level when compared to the superstructure, it is very important. So because foundation is, because for the all the earthquake forces are applied to your beams and columns, and then you take care of that, assuming that you take care of that. But the foundation is not taken care, except you are saying that there are certain, but I am saying the seismic forces are likely to be more than, please understand that, whatever you design for. So obviously there is an issue that we need to understand this slightly better. So that is what I want you to note. So it is better in my personal opinion. So I can't, even though I can't insist on this. So better to have this point, not only that is 0.18% of the gross area as a minimum investment, in order to have this, your foundation is to be safe if the building is in earthquake resistant zone. And coming to material, so we know that Indian code talks about M20 for less than 15 meter height, and M25 if it is more than 25, whatever. So, but the draft code already talks about M25 as a minimum thing. So interestingly, ACA also talks about that. So that is not a serious issue. But the question we need to understand. So forget about what are the strength is. I mean, like M20 or 25, whichever you choose, that is the lowest one. So forget about Indian or foreign. That is one thing. But what we need to understand in general as an engineer is, suppose you have a lower level of strength, you are likely to go to larger strain compared to the moderate strength where you go very less strain. And if you go to very high strength, the ultimate strain is very less than the normally not for also. So the question of understanding the material strength is not in terms of strength at all, in my opinion. So let me say that you are happy with the M20 or M25 as the case maybe as the lowest strength. More is not a problem. But if you go on increasing that into 40, 50, 60 and all those things, you should also ensure the high strength, um, uh, whether you achieved or not. And also you should also ensure the high strain is at least not 35, because not for they are talking about not 35 or not. This strain is very important because ductility is depending on this strain only. Please understand that, because your high strength, yeah, suppose you do a cylinder test strength or a cube test. So you also locate what is the strength, what is okay, that is first step. What is the strain? The strain as per Indian code is not 35 or maybe not 4 in other country codes. You should ensure that the maximum ultimate strain should be beyond this. Please understand that. So what I'm trying to say is, it is not a question of what is the strength that is given in the code. It is also important that what is the strain, ultimate strain level that your code is talking, that your material is talking about. Material is to be understood in that way only. That is the first way. Why I'm talking about this, as early as 1988, Mander said there is something called unconfined concrete, which is normal concrete, which you say not 3-5, whatever. So, but however, he says that if the concrete is confined, let me come to that confined little later. So confined, he is able to go to this ultimate strain very high, which is sigma cu. So instead of not 35, we can say 0.1, also, something like that. So let us come to number little later. So he is trying to say that confinement is very important in reinforce, because we, even though the material strain is very important because that is a basic thing to go, but if you do this confinement, you get a better strain. And that is what is going to, because one thing is very clear by now, that is the load that is going to come, and because of that the stress that is going to come is larger than whatever you computed. That is first step. The second step is, the only way of taking care of is, if the concrete has a higher strain capacity. Please understand, if the concrete has higher strain capacity, obviously this type of structure is going to survive. There is no problem, because how do you understand failure? The concrete will crack only if the strain exceeds not 35. Yes, ultimate strain increases, or even if it yields, that yield is not one, whatever. So you understand the failure or anything that happens in the concrete only by strain. Please understand that strain is a very important parameter in case of understanding the material. So, for example, let us say that these are all expression. Forget about the expression. So, the unconfined is going to be around not 4 or not 3 5 as the case may be. Confined, the safe compression can be as high as not 1 2 also. It can be more also. So, only thing is there are expressions that are given. This is given by modified matter model. That is how the stress strain curve can be thought of for concrete. And I am not asking you to look into all these formulas. Forget about it. Only thing is, let me say that in simple terms, the normal concrete strain, which is supposed to be not 35 or not 4, as the case may be, can go up to not 2 also, or not 1 2, not 1 6. We don't know what is the number that you are going to design. So that is the kind of number that you can reach. That means assuming that it is not 1 2 or not 1 6, that means the strain capacity, please understand, this is a very important thing. The strain capacity of the concrete is increased to fourfold. That is a very important thing that to happen in any concrete. So how are you going to do that? We will come to that little later. So this is the concept of ductility. The concept of ductility is we know that there is going to be something beyond elasticity is going to happen. That is inevitable and that is going to happen. There is nothing we can do about it. And for example, one of the way that we control is the spacing of shear stirrups. So the spacing of shear stirrups, I will come a little later. For example, you use F5 415, FCK as 20, FI as 415. So these are all the various strain for various spacing of shear hoops. So for example, if you keep 6 into main diameter, something that is blue line, that where you get the highest strain of nearly 0.014, something like that. So that is the greatest strain that you can ever, if you keep the spacing as 6 times main diameter, that is the way it is. This is a particular example. Don't follow this for your design because your design may be totally different. This has a lot of assumption that has made like FCK is assumed, FI is assumed, so many funny things are assumed. So don't worry about this. This is just to demonstrate to you what kind of thing can happen. Suppose I use D by 3, so the strain is now reduced to 0.013 or 0.2. Similarly, if you put 2D by 3, it is still less. And if you put D as the parameter, it's still less, not less than not 5.6. So still it is not 6. That means it is very safe as far as the concrete is concerned. So it is well within the limits of strain, all that. But what I am trying to say is, instead of putting D, if you put D by 3, the strain level goes from not 6 to not 1 2. That is twice. You please understand that. Just by changing the spacing of the shear stirrup, this is what is called confining. Confining, of course, there are so many other definitions also available, but I am making it very simple. So I am trying to tell you, if the shear stirrup is, for example, in a 300 depth thing, suppose if we keep 300 as the spacing between two shear stirrups, you are likely to get a strain which is 1/3 of the strain. If you keep just 300 by 3 is 100 mm. So you put 100 mm as a spacing, you get 3 times the strain capacity. So the strain capacity of the concrete is but stress is not that much increase, you see, minor increase only. So that is not to be taken into account as strength is increased, stress is, that is irrelevant to us. So what is relevant to us is the strain capacity. The strain capacity increasing is, so one of the important point is to get this kind of higher ductility is spacing of hoops. So you're going to design a shear stirrup. Okay, that shear stirrup, whatever be the spacing that you got through the 456 formula, whatever that formula that you are using, in addition to that, please follow this also. So for example, D by 3, that is the way that I want you to note this. And there is another important point. Now that we are talking about confinement, what is confinement? That is, within the reinforcing area, the concrete inside is fully confined. What is outside is only cover concrete. The cover concrete, if it is subjected to stress, what happens? Let us forget about it. It has no significant role to play. But what is the concrete that is playing inside this hoop, steel? This is very important. So, but suppose you keep instead of 135 degree, just 90 degree. When the strain exceeds, it may simply open up. It may simply open up and it may come out. So one of the important point that is how are we going to have this higher strain capacity in addition to spacing of hoop is to keep 135 degree as a is the thing. So when the concrete is confined and the rod is piercing inside the concrete, so even the stress exceeds, it may not come out. That is the idea. So if it does not come out, the concrete is well confined within this area. So what is more important is, suppose if you are not able to do like that, maybe you can introduce like these two things like this. So you can have one here, one like that. So or something like this. So there are so many other possibilities. How do you do is your affair, but you can't escape saying that it is difficult in the site. So I left it. So if it is difficult in the site and you left it, it will fail during earthquake. That is for sure. So the only way of saving a structure during earthquake is by keeping the spacing of chest and keeping this 135-degree hoop. These are two very important things. If you miss here, everything is missed. The whole structure may simply fail, and you no, no, I have designed as per code. It has to stand. It doesn't mean any. Those kind of arguments has no meaning at all. So that is the important issue. Another issue is because nowadays we are very happy with the Strat Pro or whatever software that you have, E-tabs, whatever. So you say that there are somebody else who is designing your structural system. So once you say 1893, depending upon zone and all, it takes the force. So it takes the force, it designs, it computes the forces, and it designs the structural system, and it designs the tension steel, it designs compress, all that funny things. Okay. So, but what are the issues in this modeling? Just a minute. But what are the issues that are there in the modeling? Okay, there are a few issues I want you to note in using the software left right. You are a user of Strat or tabs issue. It's a good thing because software is very high to a very high level compared to what we did. So there are a few issues I wanted to note. The first issue is modulus of velocity. What are we going to do? Okay, if you give some you will get it. Okay, that is number one. Keep in mind how that affects. Let us see the next one. Poisson issue. How do you take it? The code gives or that book gives. So you give that number. The third part is modulus of subgrid. That is the style has the stiffness. The style has, so the draft code really talked about all these parameters to be very serious. One of the important points is, suppose how do you do analysis? You normally say that the bottom of the column is fixed. So this is how you do it. Because you say that the soil is soft rock, whatever, because that is taken care in some other way. So I can always fix the bottom and then do analysis. Are you okay? You are not okay. Please understand that. I don't think that can happen. One is the distribution of force may not be same as what you do if you consider K value. And the two is the drift value that the compute is totally out of box if you don't consider K value. So assuming you're going to consider the subgrade action K, and again the code says, please, because the way you compute K value from the code is not a single unique number. For example, if I say concrete M40, it is M40, maybe slightly variation this side and that side. That is okay. That is with statistical means we have. But in soil, it is not like that. The soil, there can be error 100% left side, 100% on the right side. So that is a possibility in real life. In case of computing the modulus of subgrade action. So how to come out of that? Because you may know that exactly. So the way that code gives it, you say that you do the project K as one parameter, and next time you do with 0.5K, next time you do with 2 times K, and then compare all the values, and whichever is governing you take. Because when I come to take in the terms of value or the distribution that happens, I need to worry about all this. Because otherwise, no, it is not taking the correct way of understanding the forces or reactions as the case may be. So let us take a first example. Let me say that you are happy with the EC equal to 5000 root FCK, and assuming that you are considering 20. So 5000 root FCK is root 20. It is only 22,360. So this is what the value that you give in the computer. Everything is fine. So that is the first point I wanted to note. So now let's see how other country sees. For example, if you take American code, it talks about 4000 root F-she, whereas F-she is a cylindrical cell. They talk about cylindrical cell. So if you want to understand between that and this, you have to convert into 1.2. So if you do that and then find out the E value, please understand. You for the same M20, you are using an American code, the value is only 1800 and 800 MPa as against 22,360. You please understand this, because and I'm not saying American code is better, Indian code is better, that kind of thing. I am not saying anything about it. I'm just saying the way, because what is Young's modulus is to be understood throughout the world in the same way. Yes or no? Same way. Whether they use their composite strength, cube strength, that doesn't matter to me at all. Concrete is concrete. That's all over. And if you go to British code, they talk about something like 20,000 using their formula I'm just using. So the way in which I understand E value is a serious problem. So how does it matter the distribution of forces? It may not matter. Okay. But how does it matter in terms of computing drift? Yes, it affects. So let me say that you are using an American code and then say you get only 18,000 as against 22,000 in the Indian code. See, as the value is lower because the deflection is nothing but E at the bottom. So if you use American code, you're likely to get a drift value of very high. As against Indian code, you use the drift value very less. I wanted to know this. I'm not saying that no, you better use American code. That is not my contention. The way in which we understand Young's modulus is not same across the globe. And everybody is good in concrete. It is some American guy or a British guy or some other New Zealand guy or an Indian guy. So we are not interested in understanding that. What is your take on this? So your take on this is there is a possibility of E value being varying from the value that is given as physics. So better to take some lower values. For example, Indian American code says it's only 18,000. So you use an 18,000 value for M20 and try to find out what about your design. This is only to check the drift values. Whether the drift value is well within the limit or not, for that at least you give. So it is better to give a benefit of doubt for any of these Young's modulus values because it is technology is across the globe should be same. I don't think just because they use cylinders and use cubes and everything is gone. Nothing is gone because we know what is the relationship between cube and cylinder in terms of simple calculation or whatever. So what I'm trying to say is it is a serious matter than simply saying that no, I follow that, I follow this kind of thing. So if you just follow this Indian code, you are 22,000. American code is 18,800. British code is 20,000. So the drift is 19% more if AC is used. Please understand that. So if I have to understand that drift in terms of understanding drift, at least I have to run again by giving a lower value of E and then say the drift is still safe. Please understand, it is very important. I am not saying that no code is wrong, that is wrong. I am not saying anything of that sort. As an engineer, how do you understand concrete? As an engineer, how do you understand drift? As an engineer, how do you understand stiffness? This is very important because stiffness or drift or the behavior of the building is within your hands, and the technology is universal. Technology is universal. Even though there are three values, who is right? Again, we are not here to fight for that. We are trying to say that there is every possibility of E value being lower or higher, as the case may be. Higher, there is no problem because it will be less, but lower is a problem. So it is always better to give a thought like this and then introduce when you are very near to not for. When you are very near to not for, better to introduce this also and say ensure that the initial stiffness is very high. Because why I'm telling all this is because the seismic forces that are coming can be 10 times higher than whatever you are computing from code. Still, you are going to save the building only through this. This is the only way that you are going to save. So better to be careful about all this instead of arguing saying that no Indian code says everything. No code is a legal system in India or anywhere in the country. So it is not about legal system also. It is about engineering. So that way, I better ask you to think your own, apply your mind. I am not saying that you follow my idea or whatever. Apply your mind and you can follow anything. I have nothing to say about it. And that is a very important thing to follow. So that is the way it is. So now let us, now I'm not going to teach you how to design a beam, but there are issues that we need to understand when it comes to design a beam because the main idea of understanding a beam is apart from designing, because everybody wants you know the bending moment, you know MCK by mu by FCK BD square, and then you go to some percentage of reinforcement value and then get the reinforcement. I am not talking about that. I am trying to talk about how this ductility can be more or at least required by following these rules. One of the rule is the axial load, axial stress should not exceed not 8 times FCK. It's a very important thing. Where is axial stress? You may ask like that because there is no axial load in a beam. Because that is the way it is. Column only gets axial load force. But because of the seismic action, there may be an axial force. So you should ensure that the axial stress is not exceeding 8% of that. Is if you say MCK, FCK is 20 not 8 is 16, 1.6 or something. So you should ensure that the stress is not exceeding that kind of thing. So this is also important. Why it is important? Because your ductility will be low otherwise. Similarly, width to depth ratio is less than 0.3 because you don't want deep beam effect. The minimum width is 200. I'll come to that later. Indian code talks about 200 mm as the minimum width of a beam, which is, of course, I am not saying anything about that, but that is what code is given. But we should follow 100% this actually. The depth should be less than one fourth of the clear span. That is what AC309 also talks about. Don't mistake me for comparing AC309. I am not giving a high credence to AC309 and less credence to Indian code. I am not doing anything of that sort. But technology is, we should cross across the technology boundaries and then understand how everybody else understands. For example, IS456 has also introduced a draft. You may be aware of that. So that 456 talks about the beam depth, the minimum size of the beam should be 250 by 300, not the way 200 we assume in this code. So there is always revised thinking that is happening. How does it affect actually, really speaking? It affects the ductility. Please understand that. Only for, because otherwise, okay, you are for bending moment and shear force, you would have designed for the reinforcement and it is fine. I am not considering that. And if you want to say the ductility distribution of the beams and columns throughout, you should follow this kind of thing. So the beam talks about 250 by 300 and the column size minimum, they talk about 300 by 300. Even if it is three-story building, please understand that. Less than three-story, they don't care about that, but that is your affair. Because why I'm telling this, many people talk about the 230 mm as the important thing because your wall thickness is 230. I am not, but these are all the very important because we cannot confine by certain rules and regulation of an architect or funny things like that. So we are confined to understand what is engineering. So that way we need to worry about that. And another important point that I want to talk about is the minimum reinforcement. The minimum reinforcement, they talk about, for example, they talk about you give me two 12 mm bar through top and bottom. Minimum, that is what Indian code talks about. And for example, suppose I use M40 and FE415, and there is an expression that is given here. So you use that expression, and at that point of time, if I use this expression, I get 0.36% as the lowest percentage of steel. So that is okay, as I am not considering that. But that if you use 12 mm bar, if you want to be within 0.36, the beam size should be only 200 by 300. If you increase the size, they gain problem. So 12 mm bar goes out. The way I'm arguing is because code gives 12 mm bar as a minimum bar, somewhere it is given like that. So everybody says that code is giving, so I have to follow. Please understand, we are not here to follow 100% closing our eyes. Open your eyes and see every end of it. So the row minimum, so assuming that Indian code sees row minimum equal to 0.24 or whatever. So even if you follow that, it is 0.36%. But however, let us, as I told you, better to go across and see what others think about this, because this is nothing to do with the bending moment and shear force. This is something to do with the ductility. Please understand that. So the first issue I am talking about is sizes should be larger than what we governed by code. That's number one. Number 2 point is, what is the minimum reinforcement? Indian code talks about 0.36%. But however, if you take AC318, they talk about either 0.51 and or 0.48. They have two expressions they are giving. Whichever you take, no problem. So which is higher than our Indian code system. And similarly, if you go to Euro 8 also, they talk about 0.5%. So the minimum reinforcement, if it governs, please understand. The way I'm talking about it, if it governs only. If it is more than that, there is no issue. That is the first point. So the second point that I want to come here is, what is the maximum percentage? So the maximum percentage is about 4.6 says 4%. It is okay. So that is okay. If earthquake is not governing, we can't question that. Okay. But if earthquake is governing, please understand that. Even if the earthquake is not governing, wind force is only governing. But if it is in a higher zone, you should assume that it is earthquake is governing. So in all that point, the maximum reinforcement should be only 2.5% as against 4%. I am not talking this about this is to across the AC318 or whatever. I am not talking about that. But this is again to say that the ductility is more. So if you really want ductility to be more in your building, the only way to come out is lower tensile percentage, like 2.5. That means your section may increase. Okay, that you cannot just because you want to reduce the section, you can't follow 456 and say that more than 3% is allowed. More than 3% is allowed if it is not in a seismic zone. And earthquake can come, as I told you, Latur was not governed under earthquake before this code came. So the things may change. So we should worry about that also. And another important point I wanted to notice, suppose you try to find out what is moment curvature relationship of any beam, for example. So since you are interested in more curvature or more strain, as the case may be, the role of neutral axis also play an important role. Where is the neutral axis? If the neutral axis is very near to the top, you are likely to get more curvature. That means more strain capacity. And if your neutral axis is far away from the top, then you are likely to have less curvature capacity, maybe more moment capacity. However, that is not important. So what I'm trying to say is the play how where is that neutral axis is also plays a very important role in terms of getting higher curvature or higher ductility or higher strain. So this is very important. So I don't know. I have designed some tension steel. I have designed compression steel. Wherever the neutral axis is irrelevant, is not the way of talking in terms of earthquake is concerned. If it is not earthquake, I can't say anything about it. So this is another point I want you to note. Another the third point that I want you to note, because we more or less what we do is we go by Strat Pro. Strat Pro does if you give lateral load, if you give dead load and live load, if you give all the factors, it will give bending moments and shear force in all the beams and columns. You can go ahead and design. That is your concept, okay? But that is not true. I am just want to. That is not true, because at least you have to check like this. For example, if you do dead load and live load, you will get a bending moment like that, like this. That is, you have hogging bending moment at two ends and sagging bending moment at the middle. Whatever be the number, we don't care about that. That is what it is. When it comes to earthquake, for example, earthquake bending moment itself is, let me say, it is about 700 kilonewton per meter. But interestingly, this 700 kilonewton per meter bending moment that is coming only from earthquake load can create a situation where the building can sway to the right or it can sway to the left. Both can happen. So that is why we say 700 is a plus or minus, as the case may be. So both can happen. So the net effect is you should add all this, and then find out that. So the sagging, when even now it may not govern at all for the time being. But if you consider in terms of plus and minus sign for hogging and sagging, you are likely to get hogging of minus 1200 kilonewton meter and sagging of 200 kilonewton meter. So that means, so suppose if I believe this number, okay, if I believe this number, I will say I will design the tension steel for wherever tension comes, hogging at the top, whatever. So the tension steel comes, and then design this for 1200 kilonewton meter. This is simple example. Don't worry. This is not reality, okay? This is a simple example. If it comes like that, what happens? But what is the compression steel? The compression steel only 200 kilonewton per meter. So you will provide a less thing. So this is going to affect. This is going to affect either the placement of neutral axis or the placement of this thing or the ductility. So in order to come out of that, the code says you should provide 50%. So that means if the tensions that is hogging bending moment is 1200, you should provide compression steel at least for 50% of that. That is 600. So this is the code given thing. So these are, because we cannot go 100% by what is the Stat Pro or ETAPS use. So you should ensure that, or crudely, of course, if you want me to tell in a more simpler way, suppose there are 10 rods that are coming as a tension steel, the compression should be five numbers, 50%. That is okay. No, but as an engineer, you should understand what is the bending moment that comes and how it is distributed nicely. So this you should know thoroughly. But in 39 it talks about 50% reinforcement. That is, if you get 12 rods of 20 mm at the top, the bottom should be 6 numbers of 20 mm. So that is the rule that is given in 3920. You may ask why that. That is because of this. So that you should understand that, and then it is a very important thing. So the next topic I want to come is, okay, bending moment you are taking care. Only thing is the provision of reinforcement, actually 3920 governs more than your idea of getting bending moment based on the getting the steel based on the bending moment that comes. The interesting point as far as the beams are concerned, the shear capacity. It is the most important thing that can happen. I want you to know this. This is a very important thing. I want you to know this, because what is shear force? Okay, I know, because dead load and live load is given, so I know what is the shear force. And there is a, suppose assuming that there is a horizontal force that is coming due to earthquake or wind, as the case may be, there is an additional shear force. So I know all the shear force, you can go ahead. Please understand that is not so. So the current code talks about the factored shear forces as per the linear structural analysis for dead load and live load, gravity-based loads. Okay, that is okay. So factored gravity loads. The factored gravity loads means the dead load and live load as acting as a gravity load. But what is earthquake load? It's a lateral load. So it is not gravity-based. So for that, you should take the forces which, when the plastic hinges are formed both ends of the beam. So this is a very important point that I want you to note. This is what I normally miss. That is the point. So for example, what we do, For example, you take a beam, any beam in a multi-story building, you take. What you do is, assuming that you have a 1.2 times the factor, you take the dead load and live load 1.2 times the, let me say it is a uniform. So what is coming here is 50%, what is coming is 50%. So this shear force you know very well. So this is what is called gravity based shear force. Okay. What we are talking about now is, in addition to that, the bending, the due to lateral load, the two things can happen. One is the beam can sway to right at that point of time. There is a sagging moment here and the hugging moment here. And if it is left, it is hugging here, sagging here. So these two, whatever we have seen in the previous example, some numbers. What they are saying is, assume, please understand that this is a very important point. Assume that the plastic hinge has formed here. That means for whatever steel that you have provided, it is like, suppose if you have mu as a number. So what you do is mu by FCK square, you compute and then find out the percentage of steel and go ahead. Now what I am saying is, because now that you have done that, you already have what is the steel that is available in the hogging area and what is the steel. For example, let me say 10 numbers of 20 mm at the top, 5 numbers of 20 mm at the bottom. Let me say that. So that is for hogging, this is for sagging. So if you provide this, for this steel, for that section, for what that strength, what is the mu value, sagging, that you have to compute. This is what is called plastic capacity. That means you assume during the course of time, the bending moment will go to that level, that is yielding level. So what is that sagging bending moment at the left, hogging bending moment at the right? In other case, hogging bending moment at the left, sagging bending moment at the right. This you have to compute. This you have to compute. This is not available from analysis. Please understand that. This is nothing to do with analysis. Because analysis is when mu it gives a mu. I am not saying that. This is the additional thing that you have to do. So what they say is, Indian code says, the loads that are coming, shear force that are coming due to dead load and live load, which is factored already, factored. In addition to that, you should find out what is the plastic moment capacity of the sagging, hogging capacity, add them, divided by L. You know that the M plus M by L is shear force, and multiply by 1.4. This is the factor of is the additional factor of safety that they are giving. So please understand, it is very complicated for you to understand. If you are not following, we are not here to follow formulas. Okay, so there is something called sagging bending moment, which when plastic hinge forms at the left. Okay, and there is hogging bending moment at the right, which when the plastic hinge forms. You understand that? That means the hogging steel yields at the left, sagging steel at the right, add them up, divided by span of the beam, gives the shear force. That you know very well. M by L is the shear force. Again, you multiply by 1.4. That means you are trying to give 40% more force than shear force. So this is for the left case. Similarly, for other case, you have to add this. So okay, whether it is minus or plus, so you have to check for both. So this is the shear force for which you have to design. Because this shear force is not the shear force that you are getting from your ETAPS or StatPro. Because StatPro takes into account all this, but they don't take of plastic hinge formation. That is the important thing. The plastic hinge formation creates a kind of sagging moment at the left, hogging moment at the right, or the reverse wise, hogging moment at the left and sagging moment at the right. Please understand that this is a very complicated people may think like that, but it is a very simple thing. So if you design for this, because shear is very important thing, and why I'm telling is shear is a very important thing, because bending moment we are able to go here and there and then take care of that. Even if slight increase in bending moment is not going to create trouble to us, because cyclic behavior of a bending moment case is very good, but the shear cyclic behavior is very bad. That is what you have to understand from the book only. But because we cannot teach all that, so in simple terms we say that either you increase the force as per this formula. These are all not formulas, they are called empirical relationship, assuming that the beam approaches the hinges such a way that sagging on the left, hogging on the right at one time, or hogging on the left and sagging on the right at another time. Both cases you have to consider, and in these cases whichever is the worst, that is maximum shear force, in addition to this side, that is your factored. Please understand, even though there is no factor given here, this is factored dead load, live load, shear force. So this is an important thing I wanted to note, because the most of the time the building fails only because of the shear weakness. Because bending moment, the most of the time they would have given correctly, and slight variation here and there would have taken care, because maybe suppose there is a minor error in this calculation, nothing will happen, because that is still there are so many factors to take care. But shear, there is no way to take care. That is why we have to take about thing. Another important thing that I want to talk about is uh, this uh, beam, how you get anchor. Of course, code gives some formula, you have to follow that. There's no problem. But most of the time, it is not possible. Suppose one of the interesting point that happens is, suppose you finish a floor. At that point, you stop at this point with some depth given. But at that time, you want more. This length is more than this depth. So you may say that how to insert that. So either you have to take it nicely or redesign this anchoring slightly better. Why I'm telling this anchor, okay, whatever happens lately, if I make, maybe I can bend here, maybe I can bend here, still anchorage will be there. No, please don't take it like that. The joint strength, okay, in terms of ductility is very important. If the joint is kept weak, suppose you compute the length, and however, instead of keeping like this, you bend it here, that kind of thing. You say that no, it is everything is designed because anchorage is length depend on bond only, so it is fully bonded. Everything is fine. Please understand, it is not. Please understand that, because the ductility of a beam, the way in which a hinge is to be formed here, the way is to be hinge is to be formed here, you are arresting that and trying to create a weakness in the joint, and the joint fails. And so if your detailing is very bad in the joint anchorage, it is serious, I'm telling you. So this is what, this is the example I am telling. Suppose you put the concrete up to here and say I am not able to insert like that, and then try to bend like that. So that is not possible. So either you have to increase the section. So AC 318 says you better to go this kind of practice. This is the practice that is allowed in the 2000. I am not saying that you follow that. You should create an understanding in such a way that by you should only understand that even though you compute correctly the thing, that your bond is okay, and then I can bend here is a foolish idea. Please understand that. That is the only important thing. That there are empty number of solutions that is available to come out of that. I don't want to go into it. But why I'm highlighting this is, suppose you keep this as weak, so the whole building will fail at joints. As simple as that. Because you are taken care of the beam end, column end, everything you are taken care. Only this is left out. So gone. That's all. So that is the way it is. Of course, this is what our talk. This is what our code says. For example, if you are putting 8 numbers of 20 at the top, you put 4 numbers of 20 at the bottom, like that. In between, the minimum is 3 numbers of 20. If you design this, okay. If you don't design, minimum is 3 numbers of 20. That means there is a percentage that is given, like that. Similarly, for the in-between column, suppose 12 numbers at the top, as there still comes, the bottom should be at least 6 numbers of 20. That is what is called 50%. So these are all simple rules that are given in the 3920 to ensure that you don't use this formulas or something like that. You simply say that whatever the tension still you get, 50% if you keep, ductility is good, like that. So this is the way in which you have to understand. And this is the other country code, how for to avoid this anchorage, either they say go out like this in the exterior column, or introduce an anchor plate. This is what the EU8 says. I am not giving this idea to you. Choice is yours. But my point is that the joint with the kind of spacing of stirrups and the joint detailing is more important, is what I'm saying, trying to say. Because we are learning from the code how to design a column, or how to design a beam, how to detail a beam, or how to detail a column. Suppose you are able to follow 100% that, but if you are not able to do this joint, then the failure is will be at the joint. So this is what they are talking about. Now your spacing should be 150 mm, not more than 150 mm. Nowadays they say 100 mm. So lapping is prohibited in this region, because one of the point is that we assume in the design or analysis that the beam is likely to ensure likely to achieve a plastic bending moment at this point. Plastic bending moment at this point. This is an assumption that is there, because during earthquake it will happen. Okay. In order to avoid that only, we are trying to give more shear stirrups here, like 100 mm or whatever. So d by 4. We will come to that spacing little later. So in case if you put a lapping in between, at that point also you should follow this rule of 100 mm or d by 4 as a case maybe. So coming to spacing of stirrups, we are talking about 3 rules, that is d by 4, or 8 times the diameter of the smallest longitudinal. But 20 mm use means 8 into 20 is 160. That is what they say. D by 4 is depth of the beam divided by 4, or 100 mm. So most of the time, if they be these 100 mm may govern. That is the interesting point that I want you to note, because the spacing d by 4, if it is less than 100, okay, that is okay. Whichever is the lowest you have to take. So that means obviously you may end up saying that even if it is 400 mm or 500 mm depth. So let me say 600 mm depth, 600 by 4 is 150. But however, 100 mm will govern. That is the way it is. So please understand that. And also all these are all the guidelines that are given in 3920 in order to ensure that the ductility is more. This should be provided for a 2 times depth. Suppose your depth of the beam is 400, you should provide at least 1.6 meter at the end. This kind of special detailing. Of course, the draft we will skip for the timing. We are not interested. But however, I just want you to compare AC 300 also. They are also same as D/4. They are also 60 or 5D whatever. But they are happy with the 150 mm. So that is the way it is. I just want you to just cross that. However, we are restricted to Indian code, so we'll go ahead like that. So the last part in my part is the column. So we'll go a little fast big here because it is very similar to the what is in the beam. So here also the axial stress should be less than 80% of suppose the FCK is 40, 0.08 into 40 is 3.2. That much stress only allowed in the axial stress. So you should ensure that it is better to be less than that also. The factored axial compressive stress should be limited to 0.4 times FCK in all such members. This is what ASA 3 talks about. But this is very, in my opinion, this is very important because the ductility of, you have a strong column, please understand that. You should have a strong column. At the same time, the column should be ductile. It is better, the maximum stress should be limited to 0.4 times FCK. That is M40 means 16 Newton per mm square is the maximum stress that is allowed in the column with the combination of loads. These are all simple things that you have to achieve. And similarly, it talks about the dimension also. We talk about 300 mm as the lowest dimension that is there. Of course, for whatever it is there. Otherwise, you have to design as a wall or something. Here also there is another rule that is talking about one basic simple rules I forgot to mention is in any structural system, if you want to achieve higher ductility, your column should be stronger than the corresponding beam that is there. Okay, it's a very simple word that I said, but how do you implement that? So in order to do that, our this is anyhow taken from AC 319, but Indian code also talks about the same thing. There is nothing great about it. What they say is in terms of bending moment, the column bending moment capacity should be 1.4 times that of bending moments in the beam. So this is what they talk about. Suppose let me say that you have a beam coming and meeting the column. Okay, so suppose there is a beam that is coming in the column on the left side and right side. Okay, please understand that. So the total bending moment is the bending moment on the left and the bending moment on the right. So these should be added. Clear? Similarly, the column maybe top and bottom also is there. So that also we have to add. So this is called combined bending moment. Okay, the combined bending moment should be this, and your column should be having at least 40% more than beam capacity. So this essentially means, suppose you have a beam coming here, the MU is here. Okay, beam coming here, this is MU. Okay, this MU on the left, this MU on the right, add them, multiply by 1.4. That should be the bending moment capacity of the column. If it is not, you have to raise your column. Please understand that this is the only way that we can ensure that column is stronger. This 1.4 is internationally accepted number. That is, the bending moment capacity of the column is 40% more than the corresponding beam that comes. Of course, this you have to ensure in both directions. Suppose the column may come in X direction as well as Y direction. So you should ensure in both directions that happens. So the column, this is how we ensure the strong column. Because there is no way, how do you define strong column? It is very difficult to define. So international acceptance is you say 40%. So anyhow, this is taken in 2024 draft. Also, they're talking about this. We will not say go into it. So the first point that I want you to note is the column bending moment capacity. Please understand, the column bending moment capacity should be 40% more than the beams that are coming in the left plus beam that is coming in the right. That is the way it is. So the column should be stronger. This is a minimum requirement that is there. Okay. Then if you go like that, then 300 by 300 is still a series problem. Because most of the time we are misdirected by results that are coming in StatPro or ETAs. That is the way it is. No, that is the bending moment that it comes. But whatever bending moment that I am talking is capacity. Please understand that. Capacity is once you design everything, so it has a capacity. Okay, it is like working back. You get a reinforcement. From that reinforcement, find out what is MU. It is working back. So these capacities of beam capacity plus on the left, beam capacity on the right, plus into 1.4 should be the column capacity. After providing all that, you should check this. So if you don't check this, what happens? So it may come down and then fail. So that is the important thing. Okay, coming to stirrups, the stirrups is exactly same as the beam, more or less same. But only thing is, suppose if the column is exceeding more than 300 mm, what happens? So you provide in between some stirrups like this. So this is what is called confinement. This is little science only, but there is no design calculation. You cannot ask me how to compute this shear stirrup that is shown in the block. So it is, if it is more than 300 mm, you provide one. That is the only way that I can explain, because that is how confinement is. Confinement is concrete. How confined it is going to increase the strain. For example, if it is less than 300, it's okay like this. If it is more than 300, you have to introduce like this, some one additional. This is what some people call this seismic stirrup. So it's a small piece that is introduced inside the concrete. You may look, it may look funny, what is this role, this playing a role, but this playing a role of confinement. That is the thing. So that is the important thing that I wanted to note. Suppose if the dimensions are more, may you want to introduce more and more. So that means I have a simple rule for you. No concrete is left free for more than 300 mm at any place. You should introduce more than that. So this is what code says. I am talking about code only. If I were to design, I will have still less than 300. Wherever possible, it should be less than 300. But the code allows up to 300. You can allow without any steel that is coming in between. So suppose if it is 900 mm, minimum 2 3 bars should come like this. So that is the way this. There is no hard and fast rule. Same rules of this is a beam I explained. Same way in the column also same rules. Axial capacity, sagging capacity, and here instead of left and right, this is top and bottom. A and B are represents top and bottom of the column. So the shear force in the column also should be computed in a different way. So that is the main thing that I wanted to talk in this small lecture hour. But if I have some 5 minutes, I will go through very fast my experience on finding out the resilient structure. See, this Rashtrapati Bhavan is built in 1929. 1929, as you know very well. So we are asked to find out what is the seismic behavior of this. So what we did was we have taken a shaker and then driven by a motor and then controller, all that, and then we also instrumented the building with accelerometers. And then, for example, this is the elevation of the thing. We have taken this as one block and this is one block and this what is it, dome as a separate block. So the substructuring, what we call substructuring. So suppose if you take like this is taken as one substructure, this is taken as another substructure, the central portion is taken as another substructure. Like that, we have taken substructuring system. And for example, this is a dome, this is taken as a inner and outer shells, and then taken as a single subsystem. Like that, we have taken like that, and then we have taken in each of this, we have instrumented and then measured the vibration levels, and then this is how we have done a test in. I am standing here and then my colleagues are here. So this is Rashtrapati Bhavan inside, and then in addition to that, concrete, we have to use the UPV test, Schmidt-Hammer test. We have determined chlorine, sulfite, pH, and everything, whatever is possible we have did. Dr. Balasubramaniam was helping me here. So UPV tests are conducted here and there. And then our UPV results are very good, saying it is from 2.8 to 4.4. And then standard deviation is 0.4. It looks very good. So the concrete is very good, nothing to worry about. And we also taken a core, and we find the core strength is about 21 as the lowest, 31 as the highest. So assuming that M20 is the concrete they have designed, and it is okay. So nothing wrong with that, because in those days they would have designed only M20. We assume that, and for M20 we can go ahead. And the strain capacity also is not 4 or more, as the case may be. As you can see here, this is the stress strain curve of a cylinder. So this is good. And then we have taken the Schmidt-Hammer test, and we have taken powder, and we have taken everything, and everything is good. I don't want to go into all that except to say that everything is good. But the dynamic test has given me the compliance versus frequency, where I'm able to find out the natural frequency curve. So from this, this is for each subsystem. So for each subsystem, based on the compliance and frequency, I built back the dynamic system by computing the damping using this expression. Maybe difficult for you to understand, forget it. And then finding from the natural frequency, try to go to the it is like reworking. What is the stiffness work there? What is the damping there? What is the mass there? Kind of thing. So it is system identification problem. If you don't know, don't worry about that. So we identified the system, and then we try to identify the system and try to identify the then assuming that Delhi is in zone 4, for the identified system of stiffness and damping, what is the response that happens. And then we find that the Rashtrapati Bhavan is highly safe against any possible act that can happen during an earthquake as high as zone 4 or even zone 5. So the acceleration we have considered as very high. and also we have maintained that kind of high acceleration for a long time. So we say that earthquake is for seismic thing, it is very safe. So this building is constructed in 1929, which means about 90 years or over, something like that, uh, and nearly 94 years are over. So still it is resilient, and it can sustain any earthquake, and it can sustain whatever that happens in the Delhi arena. So this is the first thing, that is the way that we have to build our structures like that. Of course, for want of time, I will skip these things because I just wanted to show the Bhuj thing. Bhuj, actually, there is an hospital that failed here, and then they are able to reconstruct using uh, base isolation, and they are able to stand. So people are able to think differently in India. And we are able to look for ultra modern building with this. So at least this building will not fall during a next earthquake. But this is the Bhuj hospital that failed. So we have also alternative technologies like that, and we should also worry about some simple issues like soft stories, which are say, vulnerable. That is why we get this kind of failures in Ahmedabad and Bhuj region. And this is another soft story building that failed. And even in Japan, that there is one building, one level soft story failed wherever it is, Japan or something like that. So the soft story is a serious issue. And then discontinuous resisting elements. That is what is happening. This is how building they cut a building. So they put a column here and then they extend it to the this kind of funny things. There is not count in, even if it is only 3 stories. This building failed in Ahmedabad. So this kind of funny things, like your tank is not well connected, so it may fall. So there are issues like that. A lot of issues are there, which even the bridge column can fail if it is not confined well. These are all premature shear failure of RCPS. So these are all very important things that we need to worry about. So shear failure, as I told you, I was telling about shear computation. So this is the problem. They have not computed the shear properly, and then it failed in shear. So it is a very serious problem. In this is whatever the figure you are seeing from other country only. This anyhow, I'm just saying these things. And that is why they say that if you keep one crude rule is, suppose even in any pair, whatever, even if it is 1 meter diameter, suppose if you are able to keep 150 gap through the shear strip, this will not happen. This is what Japanese code says. There are a lot of simple rules that are available to us to still save from earthquake kind of thing, but still we have to follow that. Actually, to end, actually, I want to show my lab, which is called A-Star Lab. My colleagues will come and tell you 2 days later. And this is the lab that I've constructed when I was in service. And this is the first earthquake engineering laboratory in India of a very large scale, with an investment of nearly 30 crores at that point of time. Of course, after that also we pumped more money. So that is the way this is. Thank you so much. Thank you so much for patient listening.